Hi, calculus students. This is the first part of getting points back on your midterm, and that's taking notes in this packet along with me. It should be a yellow packet. I haven't sent it out to the copy center yet as I'm making this, but it should be a yellow packet titled AP Calculus Exam Topics to Look For, Part 1. Okay, there's going to be another part. When I tried this with people I was tutoring for the geometry test over the summer, which is a lot easier than the AP Calc test that you're going to take, but what I worked on with them, and it was successful, was identifying topics. Like one of the hardest parts, I think, about math is just knowing what you're even looking at. Like what kind of a problem is this? And a lot of times you can take a look at an AP Calc problem, which is always pretty deep problems, but you can say to yourself, this is this sort of problem. So it could be a problem involving limit techniques, differentiation techniques, integration techniques, derivative graphs. That's when we would use Susan's table. So read through this, guys. I'm going to try to make this video as short as I can, but so read through this. We're going to work on looking at a problem and automatically saying, aha, it is this type of problem. Okay, like it is a limit definition of a definite integral problem or something like that. Okay, and this is super useful with multiple choice. And the multiple choice are hard. Okay, so you take a look at that. I'm going to do some examples with you. Okay, so, all right, so limit techniques. There's these types of limit techniques. You want to look for them in this order. I'm going to do some examples, but not yet. Okay, so make sure that you're reading through these. So pause the video to read through these. So number 2, differentiation techniques. Notice I'm telling you, once we hit differentiation and integration techniques, I am saying always try power rule first. If you can rewrite the input as a sum of terms of the form ax to the n, then you absolutely want to do that instead of trying anything else. Okay, so there's that. Okay, number 4, derivative graphs, Susan's table. This should be memorized. I included some additional facts here. Okay, that would be helpful, so we should know those facts too. Particle motion or physics problems. Here's the physics version of Susan's table. And then you also want to know these things. Net change in position, otherwise known as displacement, is given by this formula. Total distance traveled, almost the same, except the absolute value of the input. And then take a look at that note that I'm giving you. Okay. Theorem identification. Okay, now this is the part where I'm going to do some examples, and you have got to take notes along with me, and that's going to be the first part of getting 3/4 points back on your midterm. Okay, now I'm not going to read through all of these theorems, but we really need to know these theorems like the back of our hand, and I'm going to work on exercises helping you to know them. Memorizing them and being able to apply them, I understand, are two different things. So you do need to memorize them, but applying them is just as important. More important, actually. Okay, so let me just, I'll just read through the first 2 so you see like how I organize this. So in this column, I have the theorem. This column are the conditions to look for. If these conditions are true in this column, then you will be able to conclude this. Okay, conclusion if conditions are true. And then here I have like a generic existence proof. All of these are existence theorems because they assert that under certain conditions something exists. Okay. And yeah, and especially in the free response, guys, you're going to want to be able to do an existence proof often. They're not going to say explicitly, like, write an existence proof for this, but you'll have to know that they're asking me to prove that this thing exists. And then an existence proof would be required for full points. Okay, so I'll just read through the first one. So the theorem, the first one I have here, and the first one we learned is the intermediate value theorem. The conditions you want to look for, there's 2 of them. Number 1, that f is continuous on a closed interval. And number 2, you'll want a value w, which would be an output value or y value, to be between the outputs of the endpoints. If these conditions are true, So the conclusion, if the conditions are true, would be this. There exists a number C between A and B. It can't be A and B, it's got to be between them, for which f of C is equal to W, that output value over here. And then a generic existence proof would look like that. Okay, now down below, so make sure you read through this other stuff at your leisure, but down below, take notes with me here. Okay, so I'm walking you through a thought process to solve this sort of problem, all right? And guys, if you can't finish this video in one shot, then, you know, pause it at certain points, but make a note to yourself, like at what time you stopped. Like if you had to stop the video here, just make a note somewhere on your paper, stopped at 5:34 or whatever. Okay, so here is an example. All right, I'm going to pretend like I'm on the AP test, and I'm going to read through this, and I'm going to tell you my thought process. And it's great. If you have a faster method than me, that's wonderful. Time is of the essence. So example, if f is continuous for a less than or equal to x less than or equal to b, and differentiable for a less than x and less than b, which of the following could be false? Okay, this is what a classic theorem identification problem would look like. So this is a theorem identification problem. Okay, so I'm going to first, okay, it would be good to read through the problem, through the choices. But even before I read through the choices, guys, if I was taking this test, I would automatically know, okay, this is what a theorem identification problem looks like. They're giving you some conditions. There's really no numbers involved. They're asking you to decide whether the statements are true or false. So they probably have a mixture of conclusions of the theorems that are above. And I'm going to ask myself, given these conditions, which theorems would apply? So f being continuous on a closed interval. Okay, so f being continuous on a closed interval, and I'm not going to keep moving the paper up and down, guys, because that might be confusing. So make sure that you're looking above as I'm saying these things. So I'm looking above at the theorems, and which of them have a condition of f being continuous? Well, the extreme value theorem, guys, the extreme value theorem, all I would need is for the function to be continuous, and then I can apply the conclusion of the extreme value theorem. Also, the mean value theorem for integrals, that one, all I would need is for the function to be continuous, and then I can apply its conclusion. Now, the other thing I'm giving is that my function is differentiable on the open interval. So I've got continuous on the closed interval, differentiable on the open interval. Which theorems could I apply if both of those conditions are happening? I could apply mean value theorem. Okay, if I just say mean value theorem, that's the one for derivatives. Okay, and look, if you don't know what I'm talking about, look above and you'll see that f is continuous on the closed interval, differentiable on the open, and mean value theorem is applying. Now, really, could we apply intermediate value theorem? I'm going to say to myself, intermediate value theorem if they're talking about a value W that is between f of A and f of B. Okay, so I haven't even looked at the choices yet, but if one of the choices involves an output that is between the outputs of at the endpoints, then maybe I could apply that, okay? Now, notice, can roles work? Roles does not work, guys, because they're not telling me that f of A is equal to f of B. Okay, so I cannot apply Rolle's theorem here. Now let me read through these. Part A, so they're asking which of the following could be false. Okay, so which of the following is not a conclusion from one of these theorems that would apply? All right, so part A, f prime of C is equal to that. This is the mean value theorem. No, it's not. Yes, it is. This is the mean value theorem, guys. Instantaneous rate of change equals average rate of change. So I'm crossing that out because that's true given these conditions. All right, they're asking which could be false. Part B, f prime of C equals 0 for some C. Guys, actually, this is the conclusion of which theorem above? This would be the conclusion of Rolle's theorem, and I already said that I don't have enough conditions for Rolle's theorem, because I would need the function value at the endpoints to be, the outputs at the endpoints to be equal. So there's the answer right there, guys. They're trying to say Rolle's theorem is true, and it's not. Now, C and D, if you look at those, F has a minimum value on that closed interval, or F has a maximum value on that closed interval. That would be the extreme value theorem, which I wrote over here that would apply. This one here, that's not exactly a theorem. It's kind of close to the mean value theorem for integrals, but an integral would exist as long as the function is continuous on that interval. Okay, so there's that. I'm going to move on. Again, if this is too much for you, this might be a long video. We've just got through the first example. So write down the time and then come back to it later. This might take you more than one sitting to get through. Okay, so there is that. Now, and guys, I'm not getting the sense that a lot of you are copying off each other this year, which is just wonderful. That shows a lot of maturity and dedication. But if a friend asks you if they could just write these things down, guys, please try to be a good friend to them and don't let them, or encourage them to watch this video for themselves. We're right now going for college credit, okay? Watching these videos and trying hard, that's what's standing between you and college credit for this course right now. Yeah, so please be a good friend if someone asks you to just write this down. That's not good. Okay, so now limit definition of a definite integral. We need to be able to recognize these two things, okay? And I'm not really going to read through them, okay? I'm going to count on you as mature people about to graduate high school that you're going to read that for yourself. Okay, now here's the example. I would take a look at this, guys. As soon as I see the limits and the summation things in my choices, I know that this is the topic that I'm dealing with. Limit definition of a definite integral. And I would want to recall, maybe even write down these formulas. Okay, I think writing them down would be a great idea. Which of the following limits is equal to that? All right, right away I'm going to try to identify the important aspects of this definite integral. Okay, I know that A is 3. I know that B is 5. Now, if you look at these limit definitions of the definite integral, we got the summation. Okay, A would go there. But where does this B come into play? B comes into play because that's what's helping you find delta x. Okay, delta x is going to be B minus A, so 5 minus 3 all over n, so 2 over n. Okay, so right now I'm going to try to narrow this stuff down. So A, whether I'm dealing with the right endpoint summation or the left endpoint summation, so the first part of the input in the function is going to be A. So that should be 3. And then I look at my choices, 3, 3, 3, 3. Okay, so I can't cross anything out there. But then I'm going to ask myself, so all the way at the end here, I should have delta x, so I should have 2 over n. So now I can cross some things out. So those can get crossed out. I should have 2 over n there, not 1 over n. Now I've narrowed it down to these two. And so I've narrowed it down to these two, and the difference between them is that here I've got k over n, and here I've got 2k over n. Well, what does this correspond to in the formulas? It either is corresponding to k times delta x or k minus 1 times delta x, depending on which of these formulas that they're using. Well, guys, this one here, k times delta x, that would be k times, our delta x is 2 over n, or it would be k minus 1 times 2 over n. So it's got to be one of these, and it would be this one, okay? So right there. If you don't see like the minus 1 in there, then they're probably using this formula. Okay, so there's that. I'm moving on. Stop the video, write down the time if you're doing this in more than one sitting. Okay, limit definition of a derivative. This is what we need to have memorized. This is the definition of the derivative, the limit definition where h goes to 0. This is the one where x goes to c. Both of these you have to know, okay? Now, if I see a situation like this, if I see h is approaching 0, h in the denominator, right away this should remind me of this limit definition, okay? So this is f prime of blank for some function. That's what that's equal to. All right, so I'm going to try to figure it out here. Now, if you're dealing with this limit definition, to the right side of the equal sign, or the minus sign, in the numerator, that is f of x, or f of the input. So actually, this one right here, this is f of some function there. And then this part right here, guys, this is f of, so that's f of blank. This is f of blank plus h. Now, looking at that, can you, and let me look at my notes from earlier. I did this earlier, so I could go fast. Okay, looking at this formula, trying to match it up to here, I see that that the function I'm working with, or that I've actually got f of 1/2 right there. That's f of 1/2, and that's f of 1/2 plus h. All right. So what I've got is 8 times 1/2, and I hope you can do this faster than me. I'm really just trying to lay it out here, but if you could do this faster than me, that's wonderful. Okay, so the function that we're working with, I'm just putting an x where I had the 1/2, is 8 x to the 8th. Okay, so really, this is the limit definition of f prime of 1/2. Okay. Now, I've identified off in my margin that f of x has to be this, so that means that f prime of x is 64x to the 7th. And I've established up here that this limit is actually the very definition of f prime at 1/2. So I could just find, I found f prime, now I just plug in 1/2, 64 1/2 to the 7th. Now, I believe that this is a no calculator one, so this might take you a moment to think about, but 64, that's actually 2 to the 6th. So it turns out, well, actually, I should have been talking about process of elimination. As soon as I identified this and this, I know that it's not going to be 0. I know that the limit does exist, okay, because the derivative exists there, and I know that this is not true. This can be determined from the information. So it's between these two, and what I just said, that's 2 to the 6th, so it's actually 1/2. Now, if you did not recognize this, guys, anytime that you're dealing with a limit, let me go back to the limit techniques for a moment. Direct substitution is your first thing that you try. So you would direct substitute 0 in for h, and you would get 0 over 0. If you got 0 over 0, then you could use L'Hopital's rule, okay, which means that the limit of this would be the same as the limit of the derivative over the derivative. So you could do it that way. If that's faster for you, by all means do that. I really think that the limit definition of a derivative, very often we can just use L'Hopital's rule to compute it if you don't recognize one of these off the bat. Okay, so there is that. I am moving along. This is going to be a long video. Pause it now if you want to pick it up later. Implicit differentiation. I didn't even bother trying to describe what an implicit differentiation problem would look like. I just jumped right to an example. It's kind of like you know it when you see it. Okay, so there's x's and y's mixed together. Y is not solved for. You are trying to find the slope of the tangent line or the instantaneous rate of change, or they'll actually say it outright, like y prime or something. So here's an implicit differentiation problem. Oh, I'm going to start telling you what's a calculator problem and what's a no calculator problem. This is a no calculator problem right here. Okay, the slope of the line tangent to the curve at that, you've got to know that the slope of the tangent line is the derivative. You've got to know that you've got to do implicit differentiation. That means that whenever you take the derivative of something with a y, you'll have a y prime at the end. Okay, that's a very not sophisticated way that I just described it, but I think that's what works for most students, so that's how I'm going to say it. It's deeper than that, though. Okay, so I'm taking the derivative of this, and I'm going to find the slope of the tangent line at that point right there. So I'm going to go super fast. This is 2y, y prime, plus this I've got to use chain rule. Okay, so inside, outside chart if you want. All right, I'm going to try to go faster than that. Derivative of the inside is, I got to use product rule right there. So it's y plus xy prime, derivative of 1 is 0. So that's the derivative of the inside. Derivative of the outside is 3 blank to the second. What goes back in the blank, what was there to begin with, equals 0. Now, if you are trying to go super fast with these multiple choices, if you try to get y prime by itself and then plug the coordinates in, I think that's going to be slower than if you just plugged these coordinates in right now. So down below, and this is how it works fastest for me actually, guys. It might work faster for you a different way, which is fine. I'm going to leave a blank for everything except y prime. Okay? Where I had an x, I'm going to plug in a 2. There wasn't an x there, there wasn't an x there, there was an x there. There was an x there, so I'm plugging in 2. I'm going to plug in a -1 wherever I had a y. I had a y in all the other spots. So that's how it works fastest for me. Okay, if it works faster for you a different way, that's fine. Now I just have to do the arithmetic and be super careful with negatives and stuff. So this is -2y prime plus -1 plus 2y prime. This is 3. Inside here I will have a -1 and I'm squaring it, so that's times 1 equals 0. -2y prime. I have to distribute that positive 3. So that's going to be -3 plus 6y prime equals 0. This is 4y prime minus 3 equals 0, so we get, and you know what? This is actually, I'm wasting time by even writing that. You know, if I were you on the test, I would just boom, go right from here to the answer. Ah, I'm wrong. Wait, am I right or wrong? I'm right. Okay, it is this. Okay, there we go. Related rates. Okay, now identifying a related rate problem is kind of hard, but on the midterm I was super impressed with some of you. I saw you writing down a no, want, when chart, and you did it at the perfect time. You recognize a related rates problem, which is half the battle when you're faced with one, is recognizing it. Okay, the radius of a circle is decreasing, so we'll have a negative rate of change at a constant rate of this centimeters per second. Okay. What is that? That is the rate of change of the radius. Okay, so I will say r prime. In terms of the circumference, what is the rate of change of the area of the circle in square centimeters per second? So a prime. This is a related rates problem because I have some rates that are related. I've got the rate of change of the radius, I've got the rate of change of the area of a circle, and the radius and the area of a circle. As one changes, so does the other. These are related rates, okay? And they are both functions of time. So everything is changing with respect to time, so we'll have to do implicit differentiation later. Always with related rates problems you will. Now I will go no, want, when. See, writing those question marks, I just wasted some time. So, okay, no. What do I know? I know that r prime is 0.1, or actually negative 0.1. Let me write that again. R prime equals negative 0.1 because decreasing. All right, if it's decreasing, that's a negative rate. They're being tricky here, guys, because they're not giving us a negative. You know, they're saying decreasing. We have to know that. What do we want? We want a prime. When do we want it? Guys, they're not telling us a certain moment when we want it, but they're saying in terms of the circumference. So for when, I'm going to say 2 pi r. I'm just going to write the formula for circumference in there, okay, instead of my when, because they're not really saying exactly when I want it, but they do want it in terms of the circumference. So I write down the formula. A equals pi r squared. We need to know that. So I write down any formulas I can come up with. Remember, for the cone problem, you also had a similar triangle one that you write down. Then you do implicit differentiation on whatever formulas you write down. If you write down more than one, do implicit differentiation on the other. But this one, I just have this. So the derivative of a is a prime equals 2 pi r prime. I'm going to leave a blank under everything except what I want. I'm trying to get a prime, so I do a prime, 2 pi blank blank. Now, what goes in for what? What goes in for r prime? Negative 0.1. What goes in for r? Guys, they want this, the area in terms of the circumference, so I've got to go over here. And so r is circumference over 2 pi. Guys, if you ever don't understand something I did, that is a moment to pause and figure out why I did it. So if this is not clear to you, you've got to pause and figure that out. You'll figure it out if you pause it. C over 2 pi, those will cancel, and there is my answer. Okay? Continuity. We need to know continuity. I don't have an example here, so I'm not going to read through it. We need to know this. Only one of you, which is not surprising. I'm not saying that in a critical way. Only one of you actually remembered how to prove something is continuous using the definition of continuity. Congratulations to the person who did. If you didn't remember, I'm not being critical. This was a very long time ago, but this is something we need to know how to use, the definition of continuity. Okay, moving on. Long video, so pause it now if you've got to pick up later. Equation of a tangent line. All right, so this comes up on almost every AP exam that I've looked at. I had to take a drink. Okay, of water. This is the equation of a tangent line, and here's the example that I chose. Which of the following is the equation of a tangent line to the graph of that at the point where f prime of x equals 1? Very straightforward what they're asking you for, but the process is not as straightforward as it could be. Most of these multiple choice, there is some element of complexity to it. Alrighty, so anytime they want the equation of a tangent line, you should know that you're going to use this formula, x minus x1. That's the point slope formula. And the point that you're going to put into it is the point of tangent, point of tangency. Then the slope is going to be f prime. All right, that's going to equal the slope. Alrighty, so which of the following is equation of the line tangent to this graph at the point where f prime of x equals 1? So right away, they're giving me the slope, that the slope is 1. And I'm going to look and see if I can cross anything out. So the one that does not have a slope of 1 is that right there. Okay, so right away you've increased your odds if you have to go back and just guess. Now the point of tangency, I need this. Okay, now I've got to find this, okay? I know that at this point of tangency the slope is 1, so the derivative is 1, so I'll take the derivative. Okay, so f prime of x is 4x to the third plus 4x. All right. I can find the x-coordinate of my point of tangency by using the fact that f prime is 1 at this point. All right. So this is going to help me find my x-coordinate. Now, guys, this actually is a calculator section 1. And something that I've got to work on with you is using your calculators, okay? A lot of times we are not using calculators when we could, and it's losing us time. So if you want to solve this equation, you can very easily do it in your calculator by graphing both sides of the equation. So I will graph the left side as 1. So y1 will be 1. That's the left side of my equation. y2 is going to be the right side of the equation. And then I can solve this equation by finding the point of intersection. Okay, so right there, it's going to be a very, very small number, but right there's my point of intersection. The way you do it, the way you get it is you go to second, trace, that's calc. Go to intersect. First curve, second curve, guess. I hit my, whatever it is, enter button 3 times. So x is 0.2 0.2367. All right, so x is 0.2367. 0.2367. Now this is a multiple choice problem, so that's why I'm estimating. If this was a free response, I'd have to store that in my calculator, which I'll review later. So that's the x coordinate. Now I need the y coordinate. Well, how do you get the y coordinate? You plug this back in to the original. Okay, so I'm just going back to my home screen. And actually, if you stored that, it might be a little bit, might actually save you some time. But I don't know. Okay, I'll just plug this in. 0.2367 to the fourth plus 2.2367 squared. And my y coordinate is 0.1152, I'll say. And now I am ready to use that formula. So y minus 0.1152 equals 1 times x minus 0.2367. So y is equal to x minus 0.2367 plus, I have to add that over to the other side, 1152, or add it to both sides. So I do negative 0.2367 plus 0.1152, and I get this one. No, I don't. Yeah, I get this one. Okay, I get D. Okay, I got D. Alrighty, guys. Now, here's another one. 13. Okay, the average value of a function. So you will need to know this information. The average value of f on a closed interval AB is given by this formula. This is the average value formula. In words might be easier to remember than the formula actually. In words, it is the area under the curve on the interval, in other words, the integral on the interval, divided by the length of the interval. Okay, so it's the integral on the interval divided by the length of the curve, or the length of the interval, which you get by b minus a. This is actually from a no calculator section. Okay, what is the average value of this function on that interval? Now, the biggest thing that people are going to get mixed up is they're going to think that they're asking for the average rate of change, which is the next one. I put these next to each other because people will confuse them because they both have the word average. They're not asking for the average rate of change on that interval. They're asking for the average value on that interval, the average function value. That's not the average rate of change. That's this one. All right, so I'm actually going to need a lot of room for this. So as soon as I identify what I've got to figure out, okay, it's going to be 1 over b minus a. B minus a is 2. The integral on the interval, so 0 to 2. And you know what? We are going to have to do u substitution, so I'm going to make sure I go x equals down there. Okay, and then x squared radical x to the third plus 1 dx. This is a non-calculator section. We definitely need u substitution. And if they're asking you to do it without a calculator, this should work out very nicely. Okay, so I go off to the side. I'm going to let u equal a function that looks to be inside of another. So x to the third plus 1. So du is 3x squared dx. All right. So dx is 1 over 3x squared du. Now, when you're doing u substitution on a definite integral, some of you have done these successfully without doing what I'm about to, but you want to get used to what I'm about to do because it's much, much faster. Now, I am going to rewrite this totally in terms of u. And I say totally because by totally, I mean also the end points here, also the limits of integration. Right now they represent x values. I want to change them to u values. So I'm going to go back over here, and I'm going to make this observation. If x equals 0, the lower limit of integration, then u equals plug 0 into what you let u equal, then u equals 1. So that lower limit's going to change to 1. And then for the upper limit, when x is 2, then u is going to be equal to 9. Okay, you just plug 2 into that. Okay, so this integral becomes 1/2 the integral from u equals 1 up to 9. And then this will be x squared. That's going to be u inside there, and I'll do u to the 1/2 to save myself time later, because I know I'll be using power rule. And then this is, so what's going in for dx is 1/3x squared du. Those are canceling. This is a 1/3. I'm going to bring it out front. So that's 1/6 the integral from u equals 1 to 9, u to the 1/2 du. Now I'm using the fundamental theorem. I bring down 1/6. I do the brackets, 9, 1. The antiderivative of this, I add 1 to the exponent, so that's going to be u to the 3/2, but then I have to divide by 3/2, so 2/3. All right? Now, I'm going to plug in 9 and 1. You don't have to plug the x's back in because we changed these to u values. This is saving so much time, guys. Really, we should practice this. So this is going to be 1/6 parentheses 2/3. 9 goes in there. Now you've got to think about this if this is not fast for you. If I plug in 9 there, a 1/2 power is like a square root, so it's the square root of 9 to the 3rd power. So that's 3 to the 3rd power, that's 27. Minus 2/3, 1 goes in there, that's just a 1. Okay, now this is a non-calculator section, so I've got to try to do some arithmetic that's going to be easy for me. For me, personally, this is easiest. If I do 1/6, factor out of 2/3, and then inside here I'll just have 27 minus 1, so I'll just have 26. These will reduce, so I have 1/9 out there and 26, so that is 26/9. You've really got to cut as many corners as you can. Alrighty guys, we are almost done. We've got 3 more examples if you want to hang in there, but otherwise just give this a pause and write down the time. Average rate of change, not average value, average rate of change. The average rate of change of a function on a closed interval is given by this. This is basically slope, change in y over change in x, slope that you're used to. Okay, this is from a calculator section. Anytime we have complicated decimals, I think it's pretty safe to say it was from a calculator section. Okay, so let f be the function defined by that. What is the value of c, for which the instantaneous rate of change of f at x equals c is the same as the average rate of change of f over that interval? This should remind you of the mean value theorem, because instantaneous rate of change equaling average rate of change, that's basically the conclusion of the mean value theorem. But anyway, so I'd like to use charts a lot. So I'm gonna over here go instantaneous rate of change, and over here I'll go average rate of change. You've got to know the difference between these. Instantaneous rate of change is the derivative. So I take the derivative of that function. Derivative of x is 1. Derivative of natural log of x is 1 over x. So f prime of c is 1 plus 1 over c. That wasn't super necessary, but they're asking for at c, so I did that. Average rate of change. Now you've got to use this formula. You have to know what average rate of change is and be able to apply it. So this is going to be f of 4 minus f of 1 all over 4 minus 1. F of 4 is 4 plus natural log of 4 minus f of 1 is 1 plus natural log of 1, but guys, natural log of 1 is 0. So I'm not even going to bother writing that down. That's just minus 1. And then this is all over 3. This is 3 plus natural log of 4 over 3. They want to know the value of c for which this equals that. So I'm going to go right to my calculator. This is a calculator section. So we want to be using our calculators. I'm going to go to y equals. Under y1, I'll go 1 plus 1 divided by x. And then in y2, I'll be very careful with parentheses and plug in that number. Okay, that's just a number. 3 plus natural log of 4 divided by 3. I will graph it and then use the intersection feature to get that number right there, okay? And you can even if you like forgot the intersection feature, you could already like say to yourself, well, that looks like more than 2. So that would let you cross out A and B. But you'll remember the intersection thing. So I go, oopsie. So I go second trace for the intersection thing. I hit enter, whoopsie, I hit enter 3 times and I get 2.164. Okay, it is this one. It's C. C. Oh, we have got 2 more. Gosh. I feel like I'm working out. I'm sweating like I'm working out. This is number 15, the net change theorem, which really is the same as displacement, okay? And I say that because we're kind of going to realize that here. Okay, so you will have to be able to know, this is the net change theorem. When they're asking for the net change of something over an interval of time, you will have to know this. The net change in a function over a closed interval is given by the integral of its rate of change, okay? So, a race car is traveling on a straight track at velocity of 80 meters per second, okay? So, velocity of 80 meters per second when the brakes are applied at time t equals 0. So the stuff that I underlined just told me that the velocity at time 0 equals 80. Okay, so that would be a good thing to write down. From time t equals 0 to the moment the race car stops, okay, but we don't know what that moment is. From time t equals 0 to the moment the race car stops, the acceleration of the race car is given by that, meters per second per second. During this time period, how far does the race car travel? Okay, so during this time period, what is the net change in position of the race car? That's what they're asking. How far does the race car travel? What is the net change in position of the race car? They're not asking for total distance traveled, just how far has it traveled. That would be net change in position. So I would automatically write this down. The net change theorem, but what would go in here is, so f prime in this situation, the first derivative would be velocity, okay? So we're basically, this is displacement, okay? Now, I know this, okay, negative 6 t squared minus t. I'm trying to get backwards to use velocity, so I gotta go backwards. So I just would take the antiderivative of this. Acceleration is the derivative of velocity. So I would just take the antiderivative. So v of t is equal to negative, using the power rule backwards, so negative 3t to the third minus 1/2 t squared plus c. We've got to find c. We can't just plug that in there. We've got to find what c is. And that's why they gave us this. Okay, so we know that v of 0, if I plug 0 in up here, I'll just get c, but I know that v of 0 is 80. Okay, so, I mean, you could do that however you want, but, so this is starting to take shape. A, the beginning of my interval from t equals 0, so the beginning of my interval is 0, to the moment the race car stops. So what goes up here needs to be the moment the race car stops. I don't know what that is. I have to think about that later. But I know that this, I now know my velocity function. 1/2 t squared plus 80, okay? dt. And now I've got to figure out the moment the race car stops. Guys, the moment the race car stops, what do you know about that moment? If the race car has stopped, something is 0. Well, what's 0? Velocity, okay? When a particle is at rest, its velocity is 0, okay? So up here, I'm going to find this. This is a hard problem. I'm going to find this by finding where this velocity function is 0, where this velocity function in here is 0. And I'm not even going to bother writing the equation down. If I know what I'm doing, I can go right to my calculator. This, by the way, was a calculator section. And I'm going to graph my velocity function, negative 3 t to the third minus 1/2 t squared plus AD, and I'm graphing it. There it is. Okay, I've got to find where that's 0. So I'm going to go, and notice it's kind of like slanting this way. Right, it's going like this way. So left bound would be above the x-axis. Right bound would be below. So I'm going to go second calc, 0. Left bound, so I want to be above the x-axis because it's slanting that way. So I'll just hit it there. And then right bound, I got to go below the x-axis. See, I'm just scrolling till my y's are negative. And then I get that. Now, I am not going to risk, rounding this. I'm going to go to my home screen, and I'm going to hit X, enter. See, that's the X coordinate that I just got from my graph. And then I'm going to store it under something. So now A is that, okay? And now, so all the way up to A. And now I'm going to go math 9 from 0 up to A. Plug in the velocity function, -3x squared minus 1/2, ah crap, it was x to the third, x squared plus 80 dx. Okay. Oh crap, it's not up there. What did I do? Crap. Shoot. Something's wrong. Oh, no. There's no way I can start this over. -6. Okay, something's wrong. I got this right earlier. I did something wrong. That is -2. Crap. You guys probably noticed that. That should be a negative, that should be a -2 right there. Okay, I'm glad I did this earlier. -2, and I'll just tell you what I got. It is B. Whew. Okay, that's B. Whoopsie. Alrighty, this is the last one. So if you can push through, I would stick around for this last one, then you'll be done. Antiderivative with an integral formula. If you know f prime of t and some value of its antiderivative, then f of t, the antiderivative of what you know, can be represented as follows. F of t equals, okay, so this formula. It's very important. The variable in the input of the integral cannot be the same as the input of f. Okay, so this, you have to change the variable here. So if it was x at the beginning, you could change it to t, but it has got to be different than this and that. Right, because the input of this function goes up there. If it was the same variable, you'd think the input of this goes everywhere. It doesn't. It only goes up there. And here's an example. A rain barrel collects water off the roof of a house during 3 hours of heavy rainfall. Okay, so maybe that's important, so I'll underline it. The height of the water in the barrel increases at a rate of this feet per hour. That's a rate, okay? So that's a derivative. Where t is in time, or where t is the time in hours since the rain began. At time t equals 1 hour, the height of the water is that. Okay, so right away, I'll let h be the height. I know that h of 1 is 0.75. What is the height of the water in the barrel at time t equals 2 hours? So I want to know h of 2 equals what? So, guys, you could say to yourself, that this is h prime of t. So if I want h of 2, I would just have to go backwards, find its antiderivative. But, guys, look at this. 4t to the third times e to the negative 1.5t. We have no way of finding the antiderivative of that. So this is a case for the antiderivative with an integral formula. Sometimes you're going to be asked to find an antiderivative value like this for something that you can't find the antiderivative of. So then you use this formula and your calculator. Okay, so I will say to myself that h of 2, all right, I am using this formula, but h instead of f. H of 2 is equal to h of the value I know, which is h of 1, so 0.75, plus the integral from the input of the value I know, so 1 up to, in this case, 2. All right, the inputs should be the same there and there. And then you could just put your rate function in here. So 4x to the third e to the negative 1.5x. And then I go math 9. Actually, I'll type it in exactly as it appears on my paper. 0.75 plus math 9. 1 to 2. 4x to the third. And then e to the negative 1.5. 2.11. Well, all right, it is D. Guys, you did it. Okay, so show me these notes, and you will be on your way to getting full points back. Not full points back, sorry. 3/4 points back on your midterm. Alrighty, guys, I will see you soon. Bye-bye.